Hi, everyone. My name is Jessie. It's really nice to have this opportunity to introduce our recent publication on JMLR. And in this paper, we propose a distributed algorithm to conduct causal inference by considering the covariance shift problem when we integrate the data from multiple hospitals. And especially, we have a focus on analyzing the high-dimensional data. And the high-dimensional data actually is very common in real-world setting, especially when we work with EHR data and also the administrative claims data. And in these data sources, we often collect a large number of covariates, and we want to capture different aspects and dimensions of a patient. So at the end, a single data set will capture, for example, hundreds or thousands of variables for each individual. And these cover the patient's information from demographics, from medication, procedure, lab results, and also diagnosis. And the high-dimensional data really give us some advantages when we generate the evidence. For example, it captures the wide range of complexity in the real-world setting, different aspects in the patient, and it makes it easier to adjust for confounding variables when we do causal inference, improve the strength of our findings, and also it gave us the opportunity to study personalized medication and also do subgroup analysis. However, there are some disadvantages and also challenges when we work on high-dimensional data. For example, when we deal with so many variables, we'll have the curse of dimensionality problems, we'll have the risk of overfitting, and also the high-dimensional data will give us the burden in the computational as well. And especially when we want to integrate the high-dimensional data in the real-world setting from multiple sites or multiple clinical institutes, there are additional challenges we need to consider. And the first major challenge is about the data privacy issue. So due to the complexity in the approval process for data sharing and also diverse law and diverse legal frameworks across different countries, across different institutes, sharing patient-level data sometimes is infeasible, especially for the international collaborations. And the other key challenge we need to keep in mind is about the population heterogeneity when we do multi-site analysis. So the population heterogeneity problem also refers as the population variation or covariance shift, distribution shift problems. And this variation should be considered, and if we ignore that, it will affect the consistency and also the comparability of the findings when we generate the evidence. So in this study, we introduced our method, which is called the DisC2o-HD, and it stands for the distributed causal inference with covariance shift for high-dimensional data. And our method has a few key features. The first feature is that it can handle the high-dimensional data for causal inference and to estimate average treatment effect using this high-dimensional covariance balancing approach. So here, suppose we can pull all of the data together. So the first step we need to do is to fit a propensity score model with this L1 penalized maximum likelihood function. And the parameter we're interested in here is the theta, and the function is Q function. And through this estimating this theta in this Q function, we can estimate the estimator in this propensity score model. And after we had these parameters, we can use that estimates from the propensity score model to further fit the outcome model. And here, this is the loss function. The L function is the loss function for this outcome model. And the parameter here is the beta. And after we estimate the beta, we can move to the step 3, which is to obtain the augmented inverse probability weighted estimator of the effect. And we can estimate the effect for the treatment group, which is tau1, and we can also do that for the control group. And after we have these two parameters, we can estimate average treatment effect by taking the difference between these two. And the good thing about this estimator is that it has the desirable doubly robust property as well. And the second great feature of our proposed method is that it is privacy preserving, because as I mentioned, in real-world setting, the real-world patient-level data sometimes cannot be pulled together. So here we leverage the surrogate method, and we want to build the surrogate likelihood function for both the propensity score model and also the outcome model. And the major idea is that we're going to take the Taylor expansion based on, for example, for propensity score model, we'll take their Taylor expansion based on this theta bar. And for outcome model, we'll take Taylor expansion at this initial value beta, the beta bar. So the idea of this surrogate likelihood function is that we're only collect the gradients here, the gradients, and also the Hessian matrix from each site to reconstruct this surrogate likelihood function, so that from this way we can protect the patient privacy, because in this procedure, only summary level statistics are required. And also, the proposed method is communication efficient by using the surrogate likelihood idea. So here is an animation to illustrate the workflow of our proposed method. So the first thing we need to do is to obtain the initial local estimate of data. And then this estimate will be broadcasted to all collaborating sites. And then each site will use this data value to compute the gradients of the Q function and also the Hessian matrix. And these summary level statistics will be sent back to the coordinating center or the lead site. And then the lead site will use these values to combine together to get the penalized surrogate propensity score estimator, the tilde theta. And this tilde theta will be transferred back to each site again, because this is the time for us to fit the outcome model. And here for the outcome model, we have this gradients of the outcome model, the objective function, and also the Hessian matrix to be transferred back to the lead site again. And after all of things will be collected again, we can calculate a final AIPW estimator and estimate the final ATE. So here in this procedure, we only need 2 rounds of communication to transfer the summary level statistics from the lead site to the coordinates to the collaborating sites, and then transfer them back. So this procedure is communication efficient because it's not a iterative procedure. Okay, and the final key feature I want to introduce about our method is that it can handle the covariate shift problems. So here you can see by using the second order surrogate method, we leverage both gradients and the Hessian matrix of these objective functions. And we want to use this idea to approximate higher order derivatives of the global objective functions. So here, by transferring the Hessian matrix, we collected them from each side. It helps us to well capture the covariance distribution and the variance of the distribution shift problem, and help us to better approximate the global functions compared with if we only transfer the gradients from each site. And to demonstrate the performance of our method, we have run some simulation studies. For example, here we consider the low dimensional settings and also the high dimensional settings. And from all of the results in the simulation studies, we can show that the proposed method can have smaller bias, smaller variance, and also smaller RMSE, which is the root mean square error, than that of the other approaches like the simple average method, or the method only collect the gradients instead of like collecting Hessian as well. And more importantly, since our method is double robust, so we also run some simulation study to work on the misclassification for a propensity score model or the outcome model. So here from this result, you can see that our method is robust enough to the model misclassification. And we also apply our method to a real-world setting where we want to investigate impact of vaccination for long COVID for the children between 5 to 11. And here the data are from 6 different sites, cover about 1,000 children. And the outcome of interest is the count of long COVID symptoms. And here we adjust for the variables like the age, sex, race, and about 200 indicators for the medical histories. And the result here is that the proposed method has closer point estimate to the pooled method, and compared with the simple average method and also the method of transferring the gradients only, our method is robust enough and can handle the heterogeneity problem. And to summarize, the proposed method is robust and also is a distributed causal inference framework, is privacy preserving, communication efficient, but only requires summary level statistics. And that's all I have. Thank you very much.